I think most people know what Pythagoras theorem is. It concerns triangles. I'll show you on the next slide. But typically what happens is people are just given it, a squared plus b squared equals c squared or something like that. And there's no proof. So we're just given it and expected to get on with it. In actual fact, there are hundreds of proofs of Pythagoras theorem, but most of them are not all that straightforward. But I've found one that is fairly straightforward, so hopefully you'll follow it. So there's only one slide to show, although it's a bit busy. So on the left hand side of this is a statement of Pythagoras theorem. Prove that a squared plus b squared equals c squared. As you can see in that diagram, there are 4 triangles. They're all actually the same triangle, rotated by various amounts. And they've got each triangle is the same, so they all have a side A, a side B, and a side C, as I've shown. And a little square in the corner there on that bottom right hand triangle just says it's a right angled triangle. So all that's happened there is we've taken that one triangle with sides A, B, C, rotated it and stuck it onto the end of the first one, and then rotated it again and stuck it onto the end of that one, and then rotated it again and stuck it onto the end of that one. So in effect it forms a big square. Now within that big square there's actually a smaller square formed with side C, because C is just the hypotenuse of that right angled triangle, a small right angled triangle. So let's prove that a squared plus b squared equals c squared. So for the big square is the square that's containing the smaller square. For the big square with sides a plus b, because when we rotate that triangle, then we add the length a to the length b. So the big square has got sides a plus b. So what's the area of that triangle? Well, it's just a plus b squared, which is the area of a square. And you work that out and it's a squared plus b squared plus 2ab. Now I'll call that equation 1 because we'll use it a little bit later. Now the area of the triangle, of any triangle, is half the base times the height. So the area of one of those triangles is a times b over 2. B is the base, a is the height, over 2, area of the triangle. But we got 4 of them. So to sum the area of all 4 triangles, it's just 2ab, because we've multiplied ab over 2 by 4. So we've calculated the area of the big square just by using the fact it's got sides of length a plus b. But we can also calculate it by summing the area of the 4 small triangles and adding the area of the inner square with the side c. So that equals 2ab plus c squared, because we've already established that the 4 triangles produce an area of 2ab. So 2ab plus c squared, which is the area of the internal square. So because 1 equals 2, in other words, the area of the square when we've calculated it as having a side of a plus b, and the area of the big square being 2ab plus c squared, because we've added all the triangles and the smaller square together, we get a squared plus b squared plus 2ab equals 2ab plus c squared. Cancel out the 2ab on both sides and you've got a squared plus b squared equals c squared. Easy, yeah? Well, it's easy if you're familiar with these kind of things, but that is one of the easier proofs of Pythagoras, that a squared plus b squared equals c squared. And finally, because it's a little bit relevant, there are integer solutions to that. So in other words, if you make a and b 3 and 4 respectively, then you'll find that you can get a right-angled triangle with sides 3, 4 and 5. There's also another one with sides 12, 5 and 13. But there are no integer solutions if the power that these things are raised to is more than 2. So there's no a cubed plus b cubed equals c cubed that has an integer solution. Fermat's last theorem, it was known as. And it took until about 20 years ago for a guy called Andrew Wiles to prove that Fermat's theorem was true. And it is true, and it's odd that only a squared plus b squared equals c squared will give integer solutions. Of course, a plus b equals c will give you an integer solution, but nothing above the power of 2. Anyway, I thought I'd add that.